Okay, so we have calculated the slope of a linear function in our previous video. Now we want to study how to calculate the slope for a more general function. Now suppose that we are sitting on a mountain with this slope again. So it would look like this. Okay. Now our coordinate is, for instance, the point A. We're sitting here somewhere, and we want to know the slope. How steep is this mountain on the place where we are sitting? Now again, as in the case of the linear function, we would look at a point a plus h. We would compare the height at that point, which will be fa plus h. We would compare it to the height f of a. We look at this difference, we divide it by this difference, and this would be our first guess of the slope that we are seeing on the point where we are sitting. Now, is this true? Well, the way to easily see it is, in fact, by drawing the line through these 2 points that we compare. And the best way is to draw it in a nice way. And then you see that the slope is not anywhere near the slope that I'm seeing here. Okay, so instead of the point a plus h, instead of the value h that we have chosen, we choose a smaller h and look at the expression we get then. So we compare our new height with our present height, these two, the difference between these two, and we divide it by h, and then we get the answer we get is then the slope of the linear function through the new point and our present position. And of course what you see is that it is already a much better guess. But again, it's not entirely true. So what we do is change this h all the time, making it smaller and smaller until it becomes very close to a, and what you get then is just, say, a sort of best fit linear function. And what is the answer? It's just that we take limits. So our guess of the slope is just by taking the limit for h to 0 of our function, and this will be, we will call our slope. Now, of course, the question is whether you can do such a thing. So let us turn this into a definition, which you can also find on page 99 as definition 4. And so, how is it defined? So we call the slope is now renamed as derivative. So the derivative of function f at the point a, because now the slope clearly depends on a, as you can see, is, we call it f prime of a, is defined as the limit for h to 0 of the value of the height of the function at point a plus h minus the height at a, and we divide by the difference of a plus h and a, which is h. Provided, of course, we can take this limit, provided the limit exists. But, of course. Now, if it exists, then we call f to be differentiable at the point A. We can have alternative notations because there are many. I will not mention them all, but one will come back a little bit later. We say instead of f prime A, we can write it as follows. So d dx of f of x evaluated at the point x equals a, and this d stands for derivative again. So you can also write it in a general way, not as a function, the derivative at a particular point a, but as a function itself, and you call it f prime x, and then we just write it as ddx of f of x without specifying the point A. It's also possible. A remark that differentiability is a refined continuity concept. So if f is differentiable at a point, so we can determine the slope, then it necessarily must be continuous at A. Because suppose that this difference will not go to 0 for h very small, this is required for continuity, then you, well, even dividing it by a very small value wouldn't would blow the whole expression up. So the derivative couldn't exist. Okay, now let me already give you a small example. We have calculated the slope for a linear function, so we get this, which is equal to the coefficient of x in the expression. Now suppose we have a quadratic function, which is still quite easily computed. So what is the derivative? We take point A, so we calculate the limit for h to 0. Well, do we need to calculate it at the point A? We just can leave it unspecified, leave x over here. So we look at the difference between the function, the height of the function at the point x plus h and x. We divide by the difference in input, which is x plus h minus x equals h. Now we plug in the formula for our function. So this is x plus h squared minus x squared divided by h. And when now write out this expression between brackets, and if you do that, then you get x squared plus 2hx plus h squared minus x squared divided by h. And now the funny thing is, of course, that the two terms with x squared cancel, and everywhere else you see a fraction where you have h in the numerator, h in the denominator, so you can take out, common factors cancel this fraction, so let me write it a little bit more extensively. We have this common factor h in the denominator and the numerator, so if we take out h in the numerator, we are left with 2x plus one term h divided by h. So it will make it a little bit more clear what happens. Now we send h to 0. Now this is what we are left is by sending h to 0 in the expression 2x plus h. Well, h becomes smaller and smaller and smaller, so we can just plug in the limiting value 0 and we are left with 2x. So what is the slope? So if you calculate the slope at the point x equals 2, then the slope is f prime 2 is 2 times 2 is 4. And if you calculate the slope at the point 3, then we get I think this is not visible anymore on our page, but I will shift it upwards a little bit. So we get the slope at the point 3 is f prime 3 is 2 times x is 3 here is equals 6. So very nice. And it makes sense. So the slope at 3 is much higher than the slope at 2. Well, if we look at the picture of the function f of x is equal to x squared, then indeed if you increase your x value, then you see that the slope becomes larger and larger. So this makes sense.